I'm going to talk to you about tornadoes. You might have heard something about hurricanes earlier today in this symposium. And in many ways, hurricanes are simple compared to tornadoes, at least with regard to what might happen in the future, right? And so that's really my focus as a climate scientist, trying to understand how storms are going to be different in the future. And so I take a retrospective look. I look at the historical record and try to understand, what might happen in the future. And so I'm going to leave you with some take-home points here. I'm going to tell you that tornado power has increased over the past few decades, in part because of the increasing heat and humidity of the atmosphere. Okay? This is really new science. This is science that has not necessarily been completely vetted. About 20 years ago, I made some claims about storms getting stronger using similar techniques. And at that time, that was fairly novel. But now we understand. We understand that as the oceans warm up, the heat engine revs up, and we can get stronger hurricanes. Again, tornadoes are not so simple. We don't have the theory like we do with hurricanes. But I believe we are getting more powerful tornadoes, and I'd like to try to demonstrate that to you. Of course, this implies greater potential for casualties, especially given that we are sprawled out more than we used to be. So what is a tornado? Unlike a hurricane, we all just experienced a hurricane, a large low-pressure system with plenty of wind and rain. A tornado is a much smaller circulation of wind, but often the wind speeds are on the order of 2 to 3 times stronger than the winds in a hurricane. So smaller in spatial scale, but more intense in terms of the wind speed. So here's some examples. So how does a tornado form? We can't really start to put the pieces together, this puzzle of what tornadoes might be like in the future, unless we start to understand how tornadoes form. And so the take-home point here is that unlike the storms that typically form here in Tallahassee during the summertime, where we get a very rapid rise of air, a big thunderstorm cloud forms, we get some lightning and thunder and some heavy rain, no tornado. The difference between a tornado-producing thunderstorm and the kind of thunderstorms we see in Tallahassee is the fact that the updraft of air that's going up to produce the cloud is separated from the downdraft, the air that's bringing the rain to the ground. And that separation of the updraft from the downdraft is due to wind shear. So we don't have a single column like we do in Tallahassee all summer, it just rains itself out. We keep the rain separated from the inflow. So the inflow separated from the downdraft, and that produces a thunderstorm that lasts for on the order of 20 minutes to a couple hours. These supercell thunderstorms are responsible for most of the tornadoes that we see. So where do they occur? Well, this dark orange here, they can occur anywhere. As soon as you get east of the Rocky Mountains, you can get tornadoes, okay, including well down here into the deep south. And so we often talk about a tornado alley, but that's somewhat a misnomer. Tornadoes occur everywhere. In fact, we had tornadoes this month, a couple days ago, up in New England. So here's the outline. Why do we think tornadoes are getting more powerful? What is tornado power? Where does that come from? How is tornado power trending? What might be causing this trend? And why is this important? I mean, that last question is pretty obvious, right? If they're getting stronger, it's pretty obvious. So this is my thinking as a scientist. We know that although the number of tornadoes is not increasing, we get about 1,000 tornadoes a year. Every year, it fluctuates 1,200, 800 from year to year, but it's not trending. But what is going up is that they're occurring in bigger bunches. So what this shows is that this is the proportion of tornadoes occurring on days with at least 4 tornadoes. Okay? This is the proportion of tornadoes, of all tornadoes occurring on days with 8 tornadoes. So although if we simply count the numbers, we're not seeing a change. But when we think about them, when we look at them as a proportion of occurring on days with at least one tornado or 5 tornadoes, we see an upward trend. So what does that tell us? It tells us they're coming in bigger bunches. And it turns out that when you have a bunch of tornadoes, the proportion that are strong actually goes up. Okay, so if you get a bunch of them, it's like someone throws a rock through a window. You're going to get a shattering of glass, and some of the shards are going to be, most of the shards are going to be very small, but they're going to be some big ones, right? And so that's the idea here. So how do we calculate the power, right? So here's a tornado damage path. This was the Birmingham tornado of April 27, 2011. From above, you can see the swath of damage that occurs. Okay, and so we can look at a couple of the characteristics that are recorded in the historical records of tornadoes. And those characteristics are, how wide is this path along the track, and then how long is it? So width and length give us some idea of how powerful it was. We also have the maximum damage that was observed. And that's a categorical variable. If there was just a little bit of roof damage, it would have been an EF0 tornado. If the whole entire foundation was blown off its foundation, if the entire house was blown off, it was an EF5 tornado. So we rank them based on the damage. So what we have in the tornado record is width, length, and maximum damage. Now, I don't know where the maximum damage occurred, but there were pockets of EF5 damage in this event. So we don't have all the information about all the details from most of these storms, so we come up with a model. So imagine now this right here, this rectangle represents that tornado path, right? That's the, and so it turns out that this EF5 tornado, only a very small fraction of that area is the worst case damage. So we're not saying that when we say that this was an EF5 tornado, we're not saying that was EF damage everywhere. In fact, most of the damage was EF0. So, but this gives us a way to say, well, if I know the maximum and I know these percentages, and I kind of do because they're pretty consistent, I can then backtrack I can say, let's integrate the wind speed over the path and get an estimate of the power. And that's what I do here. Although this doesn't come out here, this should be a summation. This is my power, and I'm multiplying. This is the weights here that I'm given. That's the proportion by EF category, and this is the wind speed. And so we're going to have this power is going to be in units of watts, okay? Or gigawatts, because it's a very big number. Okay, so 10 to the 9th watts is what we're going to measure this power. It's simply taking the summation of these wind speeds estimated from the EF damage and multiplied by the proportion of the area receiving that kind of damage. Of course, I'm multiplying by the area of the path and the air density, and that gives me this units of power. So this is kind of the money shot. This is kind of the money shot in the sense that here is our year going from left to right. We started in 1994 because that's when we had some pretty good coverage of tornado activity. This is 2017 over here, and this is my energy. This is my power. I call it energy dissipation, but it's really power. Right? Power is a same units. I'm just using it as a way to think about that power. It's dissipating its wind speed on the landscape and producing the damage. And so what you see is that it's going up. This is the average per year. This is the kind of range of that average. And this is the upper quantile of that. And each of these is going up. So when I saw this, I'm concerned, right? Something's happening. Now, as a scientist, I have to say I could be wrong that this probably isn't all due to climate change. There's a lot of other factors here. So I have to kind of try to unravel those factors. One thing I have to understand is that although tornadoes are more frequent in the afternoon, 4 to 6 p.m., that's when they occur more frequently, the power tends to actually be strongest in the evening after you go to bed. So the power distribution is orthogonal, if you will, to the distribution of frequency. So that has to be taken into consideration if I'm going to. But this then ends up to be the trend that I'm observing after I've controlled for all those other factors. Okay, so this is the trend that I believe is likely, at least partially related to the climate change. So this is my predicted from my model energy dissipation over time, and it's going up. Okay? Again, after I've controlled for those factors. So why is that? What's going on? Well, if we look at the two characteristics we have, two of them, we have path length and we have path width. This is time now going from top to bottom. This is early, this is late. This is the histogram or density plot of all the path lengths for each year. And you can see a remarkable shift. They're getting longer, they're lasting longer, they're staying on the ground longer. Okay? And and the width is not as pronounced, but there is an upward trend in how wide the damage path is too. Again, this is after I've controlled for things like changes in EF rating. I've controlled for things like El Nino effects, that shifts where they occur. We see that. So why? Well, this is my best guess at the moment. Okay. The first thing shows that the shear. I talked about the shear as a necessary component for tornado activity. The shear is increasing over time. This is the average shear on days with at least 10 tornadoes. Okay, and that's going up. So we're seeing more shear in the atmosphere. Okay. The other thing is we're seeing that the effect of the heat and moisture, which I'm calling this available potential energy. When you feel hot and humid here in Tallahassee, think of that as potential energy. Why is it potential energy? Because if you lifted that air, all that heat and moisture, you'd get rain to fall. You'd get an acceleration of the air. And that's a potential energy. And so that's increasing as a function of relative shear. So the effective CAPE on tornadoes is going up. So this is the key. CAPE is kind of flat, but the relationship between CAPE and shear is getting larger. So we're getting more sensitive to CAPE because of the increasing shear. And that's, I think that's where I am at now. And I think this is an important finding. So why is it important? Well, if I look at the casualty rate, at the per tornado casualty rate, so I'm interested in, given a tornado that produces at least one casualty, and I'm calling casualties either a death or an injury, okay? That's my casualty. The casualty producing tornadoes, I'm saying that as energy dissipation increases, the casualty rate goes up, and it goes up disproportionately depending on how many people are in its path, okay? So this is our population density, but this is going up as I just showed you. This is increasing, so we're getting further and further on this side of this diagram. Okay. Okay, so I'll leave you again with the summary. Power has increased over the past few decades. These power that I'm calculating from my data, and this implies an increasing potential for casualties. Okay. Thank you very much.